Hi, thanks for having me. I'm Omar. What I'm going to talk about is part of a screenshot related project that I haven't finished yet, but fingers crossed it will be finished soon. But part of the project involved me implementing this very specific algorithm and learning how to solve this very specific problem of looking for images inside other images. So I'm going to talk about a little bit about that now. So the basic problem is that you have two images. So you have a template, like a smaller image, and then you have a bigger image, and you want to know, like, where is this smaller image in the bigger image? Or maybe there are like multiple instances of it or whatever. And so, you want to be able to do that search. And so you kind of want to search this image, and you see that in this case, these traffic light buttons, they're over here. So we want a function that like takes these two images and gives us this location, or like a set of locations if there are multiple instances of the template inside the image. And so it turns out that you can think of this as a pretty standard image processing, signal processing operation called convolution, which you might have seen in image processing. You might have seen it in a 1D context. It's like a pretty common mathematical operation. And so the way to think of convolution is that you're basically sliding one image on the other image. So you kind of have this thing, which is like the traffic light image, and you have this thing, which is like that screenshot. And you're kind of going through every pixel in this screenshot. And that, so like we start in the top left, and then you're like looking at the area around that pixel and like comparing it to this, to the thing we're looking for. So you look at the top left pixel, and then you're like, is the stuff near here kind of like the traffic light? Then you go to the top left pixel +1, and then you kind of do that for every pixel in the entire image. So you can think of it as though you're sliding this traffic light all the way across this, across. And then what you end up with is this sort of heat map of like, okay, this part lights up. It's pretty similar. It has like a high similarity score. Maybe some of these other parts are dark because they're not so similar. And you kind of went through the whole image and like checked every single part of it. To be technical, it's like actually a little bit more complicated than convolution if you want to do this sort of image matching thing. It's actually normalized cross correlation, which basically is a convolution plus some other dividing by the average brightness of things, so that you can kind of get a reasonable comparison. Because otherwise, if you had like parts of your image that were bright white, they would wash out the parts that were black because they just have a higher average value. So there's like a little bit of extra work you have to do, but it's kind of like basically a convolution plus some other stuff is how you implement this like image matching algorithm. So, okay, so we've got our traffic light, and we've got our image that we're looking for the traffic light inside. And we do this normalized cross correlation, and we end up with this heat map, which is kind of funky looking. It's always kind of funky looking when you do these like screenshot matches. And so, you can't really see it here, but if you look for spots in the image that are like almost 100% white, like the brightest spots in the image, you'll find that basically like this spot where the traffic light is the brightest spot in the image. So you can basically just like walk through this and be like, okay, this is like really, really close to white. This must be where the traffic light is. And so, this formula, you can basically just implement this in C. You can in C or in whatever programming language, you can write a bunch of nested for loops, take in the two images, loop through the outer image, fill in all the pixels of the heat map, and you'll get something that works. Like this is kind of all you need. You can write this in C. It'll be self-contained. You take in the images, you do the math, and it'll work. You'll get that heat map, and you'll get the results. But the problem with it is that it's slow, as you can imagine, because you have like all these nested for loops. They all have to go through the entire image. Like not only are you going through every pixel in the outer image, which is 132 by 515, you're also going through every pixel in the inner image for every pixel in the outer image. So like algorithmically, it's just like not great. And we can run it live, and it actually like takes a second to run. It takes 1.2 seconds to execute, which is like a lot of time, for a computer to do this like pretty simple seeming matching. I mean, we do get the result, but it's pretty slow. So I want to make it go faster. So how do we make it go faster? I'm going to talk very quickly about what I think are like the three main things you have to do to make it run fast. First one is you want to use vectorized APIs wherever possible. So I'm on a Mac, and so I'm going to use APIs from Apple. But you may use some third-party library. You could write assembly by hand. There are various ways to do it, but you probably don't want to be writing normal for loops. because your laptop or your computer probably has like special processing support that can go a lot faster. You want to use these summed area tables to do the normalization. This is like a really cool technique that I learned about. And then finally, and like most important, you can do the convolution without actually sliding over the images. You can do it in the frequency domain using the fast Fourier transform, which is like it makes it hugely faster. Okay, so first thing, vector APIs. So yeah, Apple has this thing called Accelerate, and it has like really like a ridiculous number of functions that like let you divide everything in an image by a number or like add two images together, and you just like call these C functions and give them some pointers to your images. And some of them are like really, really specific. Some of them do like a sequence of things. And so you can kind of just like, you want to write your entire program in terms of these if possible. Second, these summed area tables. So this is really cool. So if you look at this formula, there's like, some of these are like accesses to a single pixel in the image. So like f of x of y, that's like 1 point. Some of these are accesses to a single pixel in the template. And some of these are like themselves like averages of stuff. Like this term here is like an average of a part of the image under the pixel you're looking at, which is like itself a sum of like a bunch of different stuff. And it turns out if you're computing a sum of like a bunch of elements in an array, you can make that much, much faster by pre-computing this cache. It's like kind of a cache called a summed area table. So basically, like before you do anything, you like go through your entire image, you build up a table that's the same size of the image with like running sums of all the elements in the image. So you kind of, the first thing is just the first thing, and then the second thing is the first thing plus the second thing, and then the third thing is the first thing plus the second thing plus the third thing. And then once you have this summed area table, you can just query it at 4 points, and you can get the sum of any sub-region of the image, like just with 4 operations instead of with n operations for the n things you tried to sum. This is like super useful, and it only requires like 1 image's worth of extra memory, and it's way faster. So this helps a lot for the normalization. So you can use that to get some of these other terms. There's an interesting like issue with this that's mentioned in one of the papers, which is that if your image is made out of floats, like every pixel is a float, your summed area table has to be made out of doubles, because if you make your summed area table out of floats, you get these weird precision issues. Like you just like look at it and you see these like bands going across it, which is not right. So you have to kind of go like 1 level higher, just because you're building this giant running sum and you won't have enough room if you're using the same number type as you have in your actual image. So if you have floats, you have to use doubles. I think if you're using integers, you have to use bigger integers in your table. So that's just like a weird thing that took me forever to debug. And then finally, and like arguably like the core of making this image matching thing faster, is you want to do your convolution in the frequency domain. And basically what that means is you have your 2 images, you have your screenshot, and you have your traffic lights, and you take the Fourier transform of each one. So that turns them into these weird looking images that are in the frequency domain. And then you just multiply those images together, like straight up. Like you multiply the top left point of the left image by the top left point of the right image, all the way through. Like you multiply each pixel by the corresponding pixel in the other image. And then you take the inverse Fourier transform of that multiplied image, and you get your heat map, like exactly as though you had done the kind of naive convolution that I was talking about before. So you got exactly the same result, but you only had to walk. I mean, the Fourier transform is like the fast Fourier transform is like n log n. So it's like almost as though you only had to walk each image once, instead of walking every pixel of this, and for every pixel having to walk every pixel of this. So it's way, way faster. And I can show you that now. So the slow version here ran in 1.2 seconds. And if I run the fast version, it runs in 0.03 seconds. And it gets us exactly the same result. So that's pretty cool. And that's how you can match images fast. Thanks.